Okay, so we're going to finish up our discussion on chapter 4 today. So I'm going to pull this up here, make sure everything can be seen. All right. So in class, we were kind of finishing up these examples of determining whether this is a precipitate or whether a precipitate would yield. So in this case, we would say no. We write out our molecular equation. I'll hide that real quick so that way that's not in the way. So write out our molecular equation. We have magnesium and cesium switching places. Should have magnesium and cesium switching places. I think there was some problems in this one, but when you see your molecular equation turning into your ionic equation, you can see what cancels out. You can see there's no solid forming. Let's see. Yes, that's right. This is correct. Magnesium combines with chlorine. You have your cesium and your acetate combined together. When you write out your ionic equation, you can see that everything will cancel out. You have no reaction. So no precipitate would have formed. What about in this case? Go ahead and pause the video. Try that one out. Okay, you should see a yes. So here's your molecular equation. You have potassium and sulfite combined with barium nitrate. Vitamin sulfate, actually, I apologize. You have them switch places, barium and potassium. And you have your ionic equation here. Now your barium sulfate would be SO3. It would be your solid because it's insoluble. Then you have your ionic expression down here. You can see what cancels out. So your net ionic equation would be SO3 2 minus, and barium giving you your final solid product. So we're going to try another example. Okay, so zinc chlorate, ammonium hydroxide. Yes, they do. Here's your molecular equation and your ionic equation. You can see that your zinc hydroxide is insoluble, so it will be your solid. Okay. All right, so let's look at what cancels out there. So now we need to predict acid-base reactions. So these are neutralization reactions, combining an acid and a base to form a salt and water. An ionic compound formed by a neutralization reaction is a salt. So you have an acid and a base forming your salt and water. So if we had example, we had these two, this acid and this base combining together, we would have our salt and water. Can be viewed as a double replacement reaction or a metathesis reaction. Here's your ionic equation. So you have hydrogen, chlorate ion, sodium ion, or hydroxide ion forming water, which just does not dissociate. Your sodium ion and your chlorate ion. Here's your final net ionic equation. What about neutralization? Your ionic equation, we have hypochloric acid and calcium hydroxide. Your net ionic equation again. We have hydrogen and hydroxide. Your hydroxide ion, your hydrogen ion. Water. H plus OH minus gives us H2O. True for any strong acid and strong base. Okay, so what about a weak acid and a strong base? We have our weak acid and our strong base forming water, sodium acetate. Our ionic equation. Here we have our Na plus, our OH minus. Okay. And let's see. Okay. Does that make sense here? And you might have to look at why your acetic acid does not dissociate. And that's because if we look back, let's see, our previous slide here. So you have a weak acid, which does not dissociate well in water, which is why it does not dissociate. You have your strong base, which does dissociate. We talked about before, weak acids don't dissociate very well in water, about 100%, so you would not form those ions. Okay, if we have a strong acid with an insoluble base, here's our molecular equation, our ionic equation. Our solid will not dissociate. We can remove our spectator ions. Here's our net ionic equation. Insoluble oxides, basic anhydrides. We have aluminum oxide, forming aluminum chloride and water. Our ionic equation. So we remove our spectator ions, left with aluminum oxide and hydrogen, yielding aluminum and water. What about a strong acid and a weak base? So we have ammonia and hydrochloric acid. Again, this is a weak base. Well, before we saw weak acid, but a weak base does not dissociate. Remove our spectator ions, and we have our final net ionic equation. What is the net ionic equation for the reaction below? Okay. So we have, this is our product. So this is our ionic equation. So here, be our product. And feel free to slow this down and look at these if you want to practice them. You can go back and see if you can figure these out. Okay. So here we have our double replacement reaction. Let's see, we're having our hydrogen bond here. Okay. What is the net ionic equation for the reaction of NaOH and HF? So we have a strong acid and a strong base. So you should see that you will have your final product here. So you have OH minus and HF, and then the hydrogen leaves from your hydrofluoric acid to combine with your hydroxide group to form H2O and F minus. If you wrote out the ionic equation, you would see which ones were your spectator ions, that your sodium was a spectator ion, so it's been removed. So it's not a part of the net ionic equation. Okay. Put this reaction. Determine which one is your correct product. Be D. What is the net ionic equation for the reaction of an insoluble hydroxide and a weak acid? So there's our product, our ionic equation. Our weak acid does not dissociate. Magnesium hydroxide does not dissociate. In our products, we have our hydrogen, so C2H3O2. Hydrogen is leaving, switching with magnesium to form water. We write out our, this is a solute, this breaks apart, right? And we have our ions. There are no spectator ions, so this is our final net ionic expression. So what about acid salts? So polyprotic, meaning many possible protons, your positively charged hydrogen atoms, can be neutralized stepwise. Can halt neutralization at each step. Name must specify a number of hydrogens remaining in the salt. So if we have an acid salt, the formula containing a cation, a hydrogen, and an anion. Acid salt can react with a base. Here we have sulfuric acid and potassium hydroxide forming our acid salt and water. So here we see our cation, hydrogen, and our anion sulfate. So naming acid salts. Must specify the number of hydrogens still attached to the anion, can be neutralized by an additional base. So how do we name this? This is sodium hydrogen phosphate. So what do you think this one would be? Probably dihydrogen, right? Some acid salts have common names, sodium hydrogen carbonate or sodium bicarbonate. You've seen that. You've seen bicarbonate before. You could also call it sodium hydrogen carbonate. So what about gas formation? Low solubility of gas in solvent water leads to escape of gas. Once a gas escapes, it cannot redissolve. This drives reaction to completion. Many compounds that contain anions that give rise to gases are insoluble. Adding an acid to these anions forms the gas. So, gases form CO2, SO2, NH3 by metathesis. Unstable compounds decompose and form a gas. Okay. So let's say we have reactions that form carbon dioxide. So we have an acid with bicarbonate, sodium bicarbonate, or sodium hydrogen carbonate, as we learned. And the production of CO2, water, and sodium iodide. So if we have an acid with carbonate, we have the formation of CO2 as well. Acids with sulfites and bisulfites. See examples of those. Acids with sulfides. Acids with cyanides, so form gas. And bases with ammonium salts, so form ammonia. So write the molecular ionic and net ionic equations for the reaction of LiSO3 with formic acid. Here's our molecular equation. Formation of SO2, which is a gas. Our ionic equation. So we remove our spectator ions. So SO3 2 minus. You can see our products here. Okay, if you need to go back and look at some of the principles that relating to this, you can look at those. What is the net ionic equation for the reaction of hydrochloric acid with potassium hydrogen carbonate? So you look and see which one has the correct gas. Okay. Which one has the removal of our spectator ions? We're looking at the net ionic equation. So when we do that, you should see that it is E. What is the net ionic equation for the reaction of hydrobromic acid and potassium sulfate? Sulfite, sorry. SO3 is sulfite, by the way. I think I said that wrong earlier, but it is sulfite. So what do we get? C. SO2 is our gas and water. So the overview, we have precipitation, two solutions form solid product. Neutralization, acid-base form of salt and water. Gas forming is a metathesis reaction and formed one of these products. The formation of weak electrolytes. A salt of weak acid reacts with acid to form a molecule. Predicting reactions and writing their equations. So, what reaction, if any, occurs between potassium nitrate and ammonium chloride? You need to know whether net ionic equation exists. Determine the formula of reactants. So this is potassium nitrate and ammonium chloride. We need to figure out what they make. write the molecular equation. So we have the double replacement reaction. We have potassium bonding with chlorine. Then we have ammonium nitrate. Check solubilities. All are soluble. So we have, this is our equation. We need to write out our ionic equation. Remove the spectator ions. I believe that's supposed to be there. Okay. Same on both sides. All ions cancel out. No gases, solids, water, or weak electrolytes formed. Determine the net ionic equation for the following reactions. So we have cobalt hydroxide, nitrous acid, I believe. You want to look at the name of this, make sure. So here's our products. Our solid, just because it's insoluble, hydrogen, and we have the removal of our spectator ions, should result in CO2 plus and 2H2O. Here's our product. You can pause these and practice these to figure out which one it is. If you have any questions, please let me know. Okay. Present ionic reaction when aqueous solutions of sodium hydroxide and nickel 2 chloride are mixed. So we have to figure out what is our net ionic reaction. So try this. We find that it's A. Okay, so try it out. See if you get A. Work through that problem. Okay, which of the following combinations will not react? Okay, it should be C. Synthesizing salts via metathesis reactions. Practical use of metathesis reactions. Desired compound should be easily separated from the reaction mixture. 3 principal approaches. Desired compound is insoluble in water. Start with 2 insoluble reactants. Product is isolated by filtration. The desired compound is insoluble in water. Acid-base neutralization, and reaction of metal carbonate or other gas-forming anion and acid. Product isolated by evaporation of water. So synthesizing salts via our double replacement metathesis reaction. Desired compound is soluble in water. Add acid to supply desired anion. Add excess metal carbonate to supply the metal. And carbonate reacts with hydrogen to form carbon dioxide, which is not soluble in water, and leaves the system. Metal sulfides and sulfites also work. Avoided because H2S2 are poisonous. Product isolated by evaporation of water. So what reaction might we use to synthesize nickel sulfate? Use solubility rules. Nickel sulfate is soluble in water, so there are 2 possible methods. Use acid and base, or use acid and carbonate for that product. Molarity, number of moles of solute per liter of solution. Allows us to express relationship between moles of solute and volume of solution. Hence, 0.100 molar solution of sodium chloride contains 0.100 moles sodium chloride per 1 liter of solution. Same concentration results if you dissolve 0.0100 moles of sodium chloride in 0.100 liter of solution. It's the same ratio. Okay, they both equal 0.1. Okay, so you need to know this ratio is the same as this ratio. They both equal 0.100 molar sodium chloride. So dissolved solutes make separate solutions. We mix the solutions, allow reaction to occur. We need to know the quantitatively how much of each solute was used. So we define molarity as moles of solute per liters of solution or moles per volume. Molarity as a conversion factor. Often we have stoichiometry problems involving chemicals and the volume. So we solve the problem using molarity. Molarity gives us moles of the substance or the volume of solution of substance. It provides conversion factor between moles and volume in moles per liter. So again, we see this here. It's moles per liter. So forms 2 conversion factors. We can see those. We either have one over the other. Just like the relationship we saw earlier in stoichiometry in chapter 3. 3 basic types of calculations. So we have molarity equals moles per volume. The molarity times the volume will give us moles, or the volume will give us moles per molarity. So calculate the molarity of a solution prepared by dissolving 11.5 grams of sodium hydroxide solid in enough water to make 0.50 liters. So we need to go from a gram of sodium hydroxide to a mole of sodium hydroxide to the molarity of sodium hydroxide. So we have the mass, we have the molar concentration, and we have, this is the atomic mass of sodium hydroxide, or the molecular weight, mass. And we have the molar quantity. Now we need to take the moles and divide it by liters of solution, which is given to us in the question. Get 0.192 molar sodium hydroxide. How many milliliters is 0.25 molar sodium chloride solution are needed to obtain 0.100 moles of sodium chloride? Use the molar definition. So we have 1 liter of solution. Given molarity in moles, we need the volume. So we have 0.100 moles of sodium chloride. We know that we have moles per liter of sodium chloride. Then can convert to a milliliter using the prefix, the SI prefix for milli, which is 1,000 or 1/1000. Right? We are left with 400 milliliters of 0.250 molar sodium chloride. So how about this question? Calculate the moles. How many moles of calcium nitrate are in 250 milliliters of 0.150 molar solution of sodium chloride? Use molar definition. This means 0.150 moles per 1 liter of solution. Find the number of moles. We convert milliliters to liters. 0.250 milliliters, 250 milliliters is 0.250 liters, so we already converted that. You can do that as well. And then we have our conversion. We're left with 3.75 times 10 to the negative second moles. Okay, preparing a solution of known molarity. So we weigh a solid and transfer it to a volumetric flask. Add part of the water. Dissolve solution completely. Add water to reach an etched line, which is the volume we want to get to. And we stop at the flask and invert and mix thoroughly. It's called a volumetric flask. Okay, preparing a solution of known molarity from a solid. So how many grams of strontium nitrate are required to prepare 250 milliliters of 0.1 molar strontium nitrate solution? So we first can get to moles, multiply that by the molar mass, and get to grams to figure out how many grams of strontium nitrate we need. So convert the molarity and volume to a mole. So we have 250 milliliters of strontium nitrate solution. We remove milliliters to get to liters, and then we have the molarity per liter. So it's 8.100 molar. So we have molarity per liter. So now we're left with the molarity as our final unit. Okay. This should be moles per liter, not molarity. Sorry, that should be moles per liter. It's 0.100 moles per liter. That's what molarity means. So we're left with moles, not molarity. So this should be moles. 0.0250 moles of strontium nitrate, and we convert to grams using the molecular mass of strontium nitrate. So we take SR, 2 nitrogens and 6 oxygens. 5.29 grams of strontium nitrate. How many grams of potassium permanganate must you weigh out if you want to make 250 milliliters of 0.200 molar potassium permanganate solution? So try this out. What do you get? Should get D. There's our calculation. Preparing a solution of known molarity by dilution. Okay, so we can take a solution of higher concentration and dilute it to a lower concentration. We add more solvent. The amount of moles does not change, but remains the same. So diluting solution. Moles of solute does not change upon dilution, just changing the volume. For moles in dilute equals the number of moles in concentrated. So the volume of diluted solution to be prepared. Okay, volume of concentrated solution to be used. Moles of solute in the dilute solution should also equal the moles solute in the concentrated solution. So MV diluted equals VM concentrated because moles stay the same. What volume milliliters 16 molar sulfuric acid must be used to prepare 1 liter of 2 molar sulfuric acid. So we have our calculation. Rearranging gives us V equals 1 liter times 2 molar divided by 16 molar. Give us 125 milliliters. Okay, so here's how we would prepare something like that using volumetric glassware, so on and so forth. So try this out. What do you get? Pause the video and try it out. 66. Okay. Again, pause it, try it out. 0.30 molar. Solution stoichiometry often work with solutions when conducting reactions. How do we determine the amounts needed? Just like other stoichiometric problems, we need to convert between moles. So here's our general scheme. Volume of reactant. Reactant molarity gives us moles of reactant. We use a mole-to-mole ratio. We get moles of product. We use the product molarity to get to the volume of product. So if we have a question like this, our strategy is to first go from the KOH solution, the volume and molarity of KOH solution, to get to moles of KOH. Use the coefficients from the balanced equation to get our molar quantity. Then we use the moles and molarity of H3PO4 to get to the H3PO4 solution volume. Looking for how many milliliters, so we're looking for that. So let's try it out. Here we can calculate our moles. We then can use coefficients to figure out and convert between moles of reactants and products. So now we have moles of H3PO4. We then can use the molarity of H3PO4 to get to the volume of H3PO4 in milliliters. I'm not going to read all of that, but you can read it. Any questions? So if you have 0.50 molar sodium carbonate, what is the concentration of each type of ion in solution? Okay. So we can figure out, if we have the molar value, we can figure out the concentration of sodium ions. Figure out the concentration of the carbonate ions. We know the ratio from the ionic equation. Okay, try this one out. There's the solution. So here's an example. We need to write the net ionic equation, determine the game plan. So this one's a little bit longer because we have to go from moles of FeCl2. We need to get to KOH. So in this case, we have to go from, we have this expression, and we have to be able to get to moles of KOH, or the volume of KOH. Okay. Okay. So we have to convert. You can slow this down. You can pause this and look at these, or to figure out how to get to the volume of KOH. Right. And then here, we have our net ionic equation. There's our strategy to get to grams. It's a little longer, so go ahead and pause that so you can understand how that works. If you have any questions, let me know. So we can also look at our limiting reagent. So whichever one creates the smallest amount of grams of lead to iodide. Limiting reagent problem. And 2 grams. So if we start with the other, we have 11.06 grams. So this is our limiting reactant or limiting reagent. So lead nitrate. It's limited. So then we do our, that would be our limiting reagent. Okay. Different Analytical approaches. What substance is present in the sample? Measures the amount of various substances in a sample. So qualitatively, we're just talking about what substances, period. Go ahead and read through that. Strategy is going from grams of silver chloride to grams of chlorine. Grams of chlorine, yeah. We can break that down, figure out our percentage. Write the balanced equation. We need to use this strategy. Okay. All right. Let's see our balanced chemical equation. Grams. Not here yet. And then we need to figure out our percentage. Okay. Titration is widely used. Determine concentration of solute. Full addition of one reactant. Do acid base is a very common type of titration. So if we know the polarity of sodium hydroxide and measure the exact volume of sodium hydroxide needed to completely neutralize citric acid, we can figure out the moles of citric acid and the grams of citric acid. So titration in practice, we use a burette. This is an example of a burette. Geometric measuring devices with 0.10 milliliter markings emits a flow of titrant to stop when reaction is complete. So this is, it starts turning blue in this case. So titrant is a solution of burette. It has a known concentration. The analyte is a solution being analyzed. Equivalence point is a volume of titrant where moles of titrant and moles of analyte are stoichiometrically equal. Indicator is a dye. Indicates the end point of titration. Volume of titrant required to completely react is monitored by the color change of the indicator. We would choose an indicator so the endpoints or equivalence point are the same. So we can use metric prefixes with molarity units, use millimoles, just like we did before. Milli meaning 1/1000th. Okay, this would be milliliter. That also changes. So you notice these are the same, but these units have changed. The prefixes have changed. Use the last ratio in pounds with milliliter units. Okay, so here's our example. We need to write the balanced equation. There's our balanced equation. Calculate the millimoles of base used. Calculate the millimoles of oxalic acid. Calculate the molarity. Here's our summary of all our stoichiometric calculations. So you can see them all expanded on where we were before, which was just in this area. We've now added molarity to get 2 liters of solution. All right. So we can try this out here. Try this example problem. Get E. And here, hit D. All right, there we go. So thank you so much for listening in on this video. Hopefully it's been useful for you, and we are now ready to start chapter 5. Hopefully you went through and tried some of those problems. You will see them again in your homework assignment, so make sure you go through, try them out, see what you can do with them, and let me know if you have any questions. All right, I look forward to seeing you on Monday.